Welcome to this lecture series in general topology. In this lecture, we'll introduce the notion of subspace topology, which will open up for us a whole new range of topological spaces that were inaccessible to us before. All I want to recall is a notion from real analysis. So in real analysis, if you have done a course, which is a hard prerequisite for the current, for the course on general topology that you are currently watching. So in real analysis, certainly you must have learned the notion of or the meaning of continuity of a function of this sort. If such a function is given, when do we say it is continuous? And a little bit more generally, you must have also seen continuity of a function of this sort, a function defined on an open interval. But it is possible that you may not have seen the definition or notion of continuity when you have just an arbitrary subset of reals as the domain of the function. If you haven't, that's okay, you don't need to know it. But if you have seen it, then all I want to say is that in today's lecture, we will generalize that to extreme heights. Whatever we are going to define as subspace topology will encompass this definition and a lot more. So what was the definition, or you could say theorem, depending on your definition? What was the meaning of continuity of such a function? So fix a function f from a subset S of reals, two real numbers. We say that f is continuous if for all open sets V contained in R, we have the pre-image of V is U intersection S for some open set U in R. You may have seen a definition via convergence, but that is equivalent to this. Or you may have seen some other definition. There is not just one way to define continuity, there are multiple ways. Okay, so with that, let us proceed. Some problems for practice. And now let us get started. So what is the philosophy? Well, you must have seen, again, as I said, as a prerequisite, we had linear algebra and group theory. So these two were mentioned as prerequisites. And here in linear algebra, we learn many things, but we, of course, learn the meaning of a vector space and then of subspaces. So subspaces are vector spaces contained in vector spaces, right? In group theory, we learn about groups and then about subgroups, groups contained in groups. So this prefix sub is a very important prefix in mathematics. Whenever we have a mathematical object, we can always talk about, or we should be able to, in generally speaking, talk about sub-objects. If you have a group, you should be able to talk about subgroups, copies of other groups fitting inside the original object, and similarly for vector spaces. So what we are going to or trying to achieve is a similar thing for topological spaces. Given a topological space, we want to talk about subspaces contained in them. But here, when we say subspaces, we do not want to get confused with linear subspaces. These are topological subspaces. It turns out that the situation in the case of topological spaces is much, much simpler. In linear algebra, you cannot pick an arbitrary subset of a vector space and try to think of it as a vector space. Not all subsets assume vector space structures. Similarly for groups. But in the case of topological spaces, any subset of it can be genuinely regarded as a topological space in its own right. And that is what we are trying to explore. I have broken the discussion down in two lectures. So today we will basically deal with the topology aspect. And in the next lecture, we will explore the continuity aspect. Things will become clear as we go along. So we will define what is meant by subspace topology, namely the topology on a given subset of a topological space. So what is the guiding principle? What are we trying to achieve? We can define arbitrary topologies on a given set. You pick a set, you can endow it with the discrete topology or the indiscrete topology or some other messed up topology. But whatever is our definition, it should respect the parent. We have a topological space X. We have a topological space X and there is a subset of it given to us. We are trying to define a topology on it, but whatever be the topology, it should have some relationship with the parent. We cannot just give it some arbitrary topology and hope to get anything interesting or useful. So the guiding philosophy would be, we have a topological space, we have a subset of it. We want to define a topology on A so that at least the following should happen. We need a little more, but at least the following should happen. That if we have a map, if there is a map from some topological space Y to A, then if, even before I say that, even before I say this, we want to define a topology on A such that the following should happen. The inclusion map should be continuous. Right? Just like in vector spaces or groups. You have a linear subspace of a vector space V, the inclusion map is linear, right? If you take the inclusion map, it is linear. Similarly for groups. If you have a subgroup of a group G, the inclusion map is a group homomorphism. And the analog of linear maps or homomorphisms in the setting of topological spaces are continuous maps. So we would naturally like to ask that the inclusion map be continuous. But of course, just asking for this much is too little to ask, because you can always endow this with the discrete topology and then the inclusion map and every other map would then be continuous. So that would be not useful. We would like to say a little bit more. We would like to say that if we have a map from a topological space Y to A, suppose we want to check its continuity, it should be enough to consult with the parent, compose with the inclusion map, and ask if the composed map is continuous. If the composed map is continuous, then we would like to say that this is also continuous. That is the kind of topology we want to give to this guy. Right? That's really what we want to get at. And in fact, that would be the way to define it. Like we should really define it that way. But I would take the more traditional route, the way it is usually presented in textbooks. We will write down a topology, and then by the end of this and the next lecture, we will see that this philosophy has been fulfilled. Okay, so now I'll define I'll write down the definition of the subspace topology. Whatever I said here, you can keep it at the back of your mind. Okay, it's not like what I'm going to write will immediately reflect upon this. So, we have a topological space, we have a subset of it, we define the subspace topology on A, and again, I want to stress that this word, this reappears or this appears in linear algebra. Don't get confused. This has nothing to do with linear algebra in this context. Okay, so the subspace topology on the subset A of X is defined as the following set. You consider all these intersections where U is an open set in X. Right? Very simple to write it down. Nothing very complicated. And it's your exercise. Check that this is indeed a topology. Okay. So we have defined the subspace topology. Every subset of X now has a right to throw maps and ask if those maps are continuous, and receive maps and ask if those maps are continuous. Okay, and we will see that this will be very useful. So we have defined really the open sets in the topology on A, because what is the definition of a topology? It is just the collection of all the open sets. It's actually the other way around. First you define the topology and then you define open sets, but whatever. So what are the closed sets in this guy? We know what are the open sets, what are the closed sets in it. So you fix any subspace of X. So yeah, so when we say A is a subspace of X, what does this mean? A is a subspace of X. This phrase means, first of all, that this is the topological space, and that this is a subset of X, and that this has been endowed with the subspace topology. Also, whenever we take a subset of a topological space, and we don't mention anything about the topology on it, we will implicitly assume that it has been endowed with the subspace topology. Just like when we were discussing products, if you have two topological spaces and you take the product, if we don't mention anything extra, we naturally assume that the product has been endowed with the product topology. Similarly here, every subset of X, unless otherwise mentioned, will be endowed with the subspace topology. Okay, so A is a subspace of X means that A is a subset of X endowed with the subspace topology. And then the closed sets in A are precisely the sets of the form F intersection A, where F is closed in X. This is a trivial remark because what happens? What are the closed sets? Complement of open sets, meaning complements of these kinds of set. So if you take the complement of this in X, what do you get? The complement of that in X is this thing, which is what? Which is nothing but this intersection A. So, sorry, I wrote something wrong. What I meant was this thing. I misspoke. I said complement of this in X. Sorry, I wanted to say complement of this in A. We want to say complements of open sets in the topological space. The topological space in question is A, right? These are the open sets in A. We want to find out what are the closed sets in A. So we will take complements of open sets in A. So we are trying to figure out what is this thing. In my mind, it was A, but I wrote X. So we are trying to find what is this, but this is just basic set theory. This is nothing but X minus A and X minus U intersection A. And X minus U are precisely the closed sets in the parent space X. And maybe I'll just draw a diagram for clarity. So this you think of as X. And here we have A. Maybe I'll make A a little more civilized. This is A. And then we have an open set of X, call it U. And the complement of this intersection in A is this region. What we are saying is that it is same as you take the complement of U in X. Take the complement of U in X and intersect with A. That is same as the complement of A intersection U in A. Okay, so I'm saying something purely set theoretic. At any rate, you can easily prove this for yourself. It's just a very small remark. Admittedly, right now the discussion is very abstract. We have given a bland definition and we will be able to appreciate it only with the time. Okay. So let's talk a little bit about continuity in the context of subspace topology. This will be explored more fully in the subsequent lecture. So fix two topological spaces X and Y, and suppose A is a subspace of X. And suppose we are given a map from A to Y. Maybe I'll draw a picture. So here is our topological space X. And we have a subspace of it. Okay. And we are given a map from A to Y. This is A, and I will draw Y a little bit more funky. Yeah, okay, that will do. Okay, that is the situation. A has been endowed with the subspace topology coming from the parent X, and fix a point little a in the space capital A. So here we have a point little a. When do we say that f is continuous at the point A. So this is just a matter of unraveling the definition of the subspace topology and that of continuity at a point. Right? And this is just a remark. This is not some theorem or anything. So f is continuous at A if and only if for all neighborhoods V of Fa in Y, there is a neighborhood O of A in A such that f of O is contained in V. So I haven't done anything. I have just written the definition of continuity at a point. But we want to write something which has some relationship with X. This is purely about A, right? So just writing the same thing and noticing what is meant by neighborhood of A, just by using the definition of the subspace topology, we can rewrite the same thing as for all neighborhoods V of Fa in Y, there is a neighborhood U of A in X. U of A in X such that f of U intersection A is contained in V. So I've just rewritten the previous thing. Using the definition of the subspace topology. Okay. I'd like to make one more remark. Right, so this time we are asking for global continuity of the function f, not just continuity at a point. So the situation is the same. We have a topological space X, we have a subspace of it, we have another topological space Y, we have a function from A to Y. We are asking what is the meaning of f being continuous. So f is continuous if and only if, just unraveling the definition of the subspace topology. For all open sets V in Y, or open set V of Y maybe. Let me write in Y, we have S inverse V is open in A. So it's just a repetition of the definition of a topology in a purely abstract fashion. But if we want to reference the parent, we would say that is for all open sets V in Y, we have S inverse V is equal to U intersection A for some open set U in X. Okay. So we have a very simple way of looking at continuity when the map is defined on a subspace of a given topological space. If we have a good understanding of the parent, we should not have much difficulty in deciding when such a map is continuous, although it will be little bit of a task in many cases. Okay, let's proceed. Yeah, so as we recalled in the beginning of this lecture, just give me 1 second. Yeah. So as we recalled in the beginning of the lecture, there is this notion of continuity of a map defined on a subset of reals to the reals. And I will repeat it because you may have missed the recap. So for a function f defined on a subset of reals, f is said to be continuous if, and this is what we learn in real analysis, so if for all open sets V in R, we have F inverse V is equal to U intersection S for some U open in R. So this is what we learn in real analysis, but if you didn't learn this doesn't matter, because if you endow S with the subspace topology from R, this is exactly the definition of continuity that you get on the map F. So regardless of whether you learnt this particular thing in real analysis, we have recovered it by our framework of subspace topology. Okay? And here is something that I want you to work out, just in case you didn't do it in real analysis. So we have a function from the punctured reals to reals. When I say punctured reals, I'm just saying that take out 0 from the reals. So we have such a map, and now we can talk about its in the framework of general topology. We can ask whether or not such a map is continuous. Previously, we couldn't do it because we did not have a topology here. Now we do. So we can talk about the continuity of it in the framework of general topology. And as we just mentioned, it does not conflict with what we already learned in real analysis. So we can, in some sense, forget about real analysis now. As far as the continuity aspect goes, differentiability and integrability and all those things remain. But as far as continuity goes, we have outgrown the baby steps that we took when we learned real analysis. Everything now we can think in the bigger framework of general topology, much bigger, I would say. Okay, so now we can talk about the continuity of this map. And suppose we have this definition, fx going to 1 by x, which is well defined because 0 is not in the domain. Then f is continuous. And here I've attempted to draw the graph of the function, even though I did not draw the left side. I was being a bit lazy. Okay, so yeah. This is something that you should do. This is a very simple exercise, just a matter of following the definition, right? So very important exercise. If you don't recall this from real analysis, in fact, I would suggest go back and revise or learn real analysis well and then come back. But you can maybe spend some time here also. Okay. So now let's look at some examples. First of all, we'll look at intervals. So the simplest interval to look at would be the open interval. So suppose we have this open interval contained in reals. What are the open sets here? The open sets here are what you obtain when you intersect this with open sets in reals. But open sets in real numbers are themselves just union of intervals, right? Or union of open intervals. So the open sets here look like this, things like this, just small intervals contained in it or unions of them, right? So the subspace topology here is pretty simple. It's boring. It doesn't give us anything new. But the situation changes if we look at closed intervals. So suppose we have a closed interval. Now, of course, these are still open sets in the subspace topology, because this thing that I've just drawn was open in the set of reals, and if you intersect it with this interval, this closed interval, it will be open in the closed interval also. But what about if we take this open set in the set of real numbers, this is open in the set of real numbers, and intersect it with our closed interval? What do we get? We get just this thing. This thing is not open in reals, but it is open now in the closed interval, right? So the sets of this form, I don't know how else I can explain this, but these things, these things are now open in this topology, in the subspace topology. These were not open in the original topology on reals. Okay, so something extra has happened, something new has happened, I should say. Okay, and you can similarly think about half open intervals. I mean, whatever we said for the left side, we can also say for the right side, right? And you can think about half open intervals and so on. Okay. What about this thing? What is this, first of all? This is, by definition, all those points in the complex plane, in the two-dimensional plane, or in the Euclidean plane, which are at a distance of 1 from the origin. So it's a very familiar object. It is just a circle of radius 1 centered at the origin. Okay, something like that. We can also write this as follows. It is the same as all those complex numbers whose magnitude is 1. And this is a very usual way to look at S1. It's exactly the same as the previous one once you think of the complex plane as R2, because you can always do that. And this is just the magnitude of it. So this is nothing different. It's exactly the same description. But it is often helpful to think of S1 as this rather than that, because there is a multiplication that is here. You can multiply complex numbers. And if you multiply two elements of S1, you again get an element of S1, right? If you multiply two complex numbers of magnitude 1, you again get a complex number of magnitude 1. Okay, great. So what are the open sets here? Well, the open sets here are what you get when you intersect this guy with open sets in R2. And particular open sets in R2 are just balls, these open balls. So certainly these patches, these arcs, things like these are open in S1, and unions of them. You can take unions of them. For instance, you can take these two and take their union. That is also open in S1, of course. So such things are open in S1, and that gives us some idea about the topology on S1. Some intuitive idea, I mean. We know exactly what the topology is in the technical sense, but we also need to get an intuitive hold on it. And it is not hard to get an intuitive hold on it. In the next lecture, I want to also talk about functions from S1 to some other space, and when can we say they are continuous. You take some concrete examples and so on. That will develop further intuition. But for now, this much I think is fine, that these are the open sets. And we have some idea what is meant by nearness. Okay. Then we have this guy Sn. What is Sn? Sn by definition is those points in Rn plus 1 which are at a distance of 1 from the origin. So it is an immediate generalization of S1. If you substitute n equals 1, you get that object. And here you can't do any complex number fishy business. Okay. So it's just the two-dimensional version of it. If you take n as 2, you get something like that. Something like that. Right? So this is what you get when you... And this is the hollow sphere. Nothing is inside and nothing is outside. It is like the ping pong ball. And what are the open sets here? Well, difficult to draw. But again, if you intersect it with open balls in R3, this is sitting inside R3. The parent of this guy is R3, right? It is a subset of R3. If you substitute n is equal to 2, you get R3. So if you intersect this thing with open balls in R3, you get, small disc-like, curved disc-like patches. All of those are open and unions of them are open. And here the open sets are far more complicated, or can be far more complicated than here, because this is a two-dimensional situation. Just like open sets in R2 can be quite complicated. Okay. So that's the n-dimensional sphere. So we should know the names of them. So this is the n-dimensional sphere. Now we haven't talked about dimension or topological dimension. So you can just call it the n-sphere, and that's perfectly fine. This is the n-sphere, and this is just called a circle. You can call it the one sphere, but nobody does that. Okay, then we have D2. D2 is what? D2 is all those points in R2 which are at a distance of at most 1 from the origin. So the picture would be something like that. And what are the open sets? Well, obviously patches like these are open, these things are open, but these things are also open here. Because how do we get that? We just intersect this open ball in R2 with the closed disk. I might refer to this as the closed disk, because this is a closed subset of R2, right? You should be able to now prove immediately that this is a closed subset of R2. So this, along with this curvilinear part, this thing is open in this disk. There are, of course, many other open things, but just some feel for the topology on it. And we have the higher dimensional analog of it. This is all those points in Rn, which are at a distance of at most to 1. When I say distance, I meant Euclidean distance, because we have defined other distances. So here everywhere, this is clearly talking about Euclidean distance. I've written out the description. I haven't used the notation. But yeah, so whenever I was saying distance, I meant Euclidean distance, d2, as we defined. So some new topological spaces have popped up that were not available to us previously, but certainly we wanted to talk about them. We certainly want to talk about continuity on spheres and disks and circle and intervals and many more things which will come as time progresses. But we have been able to inculcate at least some of them. Okay. So now, naturally, we would like to ask if there is some relationship between the basis or a given basis on the parent with a basis on the subspace. So precisely, suppose X is a topological space and A is the subspace of it. And suppose we are given a basis for the topology on X. Again, what does that mean? That means it is a basis on X which generates the same topology that X came with. Okay, so we have a basis for the topology on X. Can we use this to write down a basis for this guy? That's the question, and the answer is yes, and the answer is also very simple. Just define this guy as what you obtain when you intersect each element of script B with the subspace. What you get is a basis for the subspace topology on A. So, which means two things. It first of all means that it is a basis on A, and secondly, the topology that it generates is same as the subspace topology. Okay, perhaps this requires me to deliver a proof, although it is very simple. So let's check if this is a basis. Clearly, the union of all the things in this guy, let me use a notation. Yeah, what is a good notation? Let me just say it in words because I can't choose a notation. If you take the union of all the things here, you get A, right? Because if you take the union of these things, it is basically taking the union of these things and then intersecting with A. The union of all these things is the entire set X because this was a basis for the topology on X. Okay, so the other property is what we want to verify. So suppose B1 intersection A and B2 intersection A are two arbitrary elements of this object. Assume they intersect in a non-trivial way. Assume this is not empty. What do we want to do? We want to show that if you choose a point in the intersection, so let's do that. Let A be in the intersection. Okay. What do we want to do? We want to show that there is some element here which contains this guy and is contained in the intersection. But note that this implies in particular that A is contained in the intersection of B1 and B2. Right? Because what is this intersection? This is the intersection of B1 and B2 and A. Okay? So we don't need to do anything. I mean, it's just that, okay, there is one little thing that we need to do. So A is in B1 intersection B2. Now the fact that this is a basis on X gives us, it implies that there exists some element here such that A is in B, which is contained in this intersection. right? This is where we use the fact that this is a basis. And now, clearly, now A is contained in B intersection A, which is contained in the intersection of these two gentlemen. And this is a member of that guy, because this is a member of B, right? So the fact that this is a basis has been verified. Now we want to say that the topology generated by this is same as the topology, the subspace topology on A. Okay? Now clearly the topology that this generates on A is coarser than the subspace topology. I'm not saying it is strictly coarser. I'm just saying that it is coarser because everything here is already open in the subspace topology on A, because every element of script B is open in X. So clearly the topology that this generates is coarser than the subspace topology on A. Maybe we'll set up a notation. So let tau A be the subspace topology and theta A be the topology generated by this basis. Okay? We already know, so we just saw that the topology generated by this basis is contained in the subspace topology for a very simple reason. All right, so we want to show that this is actually an equality. Okay. Yeah, so want to show that this is an equality, which means we want to show the reverse containment. So to do that, fix any element in any element in tau A. So E in tau A. So what does an element in tau A look like? We know it looks like U intersection A for some open set U in X. Correct? We just picked an element here, called it capital E. We want to show it is here. But an element here looks like this. That's the definition of the subspace topology, where U is an open set in X. Okay? But now, since script B was a basis for the topology on X, this can be written as the union of some elements of script B. So, say U is the union of some elements of script B. Right? All we are saying is that there exist elements from script B indexed by some set J, such that if you take their union, you get U. Immediately from the definition of a basis, such B alphas exist. I mean, I shouldn't say the definition of a basis. I should say the fact that the topology generated by this basis is same as the subspace topology implies that such B alphas exist, right? Because the topology generated by this basis is precisely what you get when you take the unions of the things in B, arbitrary unions. Anyway, so this I'm sure you know because we beat it down so many times. So we have that. So what is U intersection A now? So what is E? So this implies that E, which is U intersection A, is nothing but this union. I'm skipping a set theoretic step. Right? If you take the intersection of this with A, you get that. Now each element here is in this thing. And if you take the union, this thing is in the topology generated by this basis. We are taking union of some things in this basis. So this whole thing is in the topology generated by this basis. And hence, this is in theta A. Right? So we picked something in tau A and showed that it is in theta A. So we have showed this orange thing. and therefore we are done. So it was an exercise in set theory, nothing going on. But I want to encourage you to draw some pictures. To draw pictures. So what do I mean by that? I mean that you make some blob, call it X. Make some blob, call it A. And then whatever we are writing here in formulas, try to draw pictures and see. Okay? All right. Okay, we are not done. A natural question arises. We have a topological space X. Suppose we take a subset of it, call it B, and we take a subset of that, call it A. Now, this is a subset of X, so we can endow it with the subspace topology. This is also a subset of X, so we can endow this with the subspace topology coming from X. But this is also a subset of this set B, which is also a topological space under the subspace topology borrowed from X. So here there is another topology, namely the subspace topology borrowed from B, not from X. Right? So what I'm trying to get you to appreciate is that A can get its topology from two sources. Either it can think of itself as a subset of B and borrow subspace topology or assume the subspace topology from there, or it can not notice B and just look at X and say, hey, tell me your topology, and then assume the subspace topology there in that way. Potentially, it might get two different topologies, and that would cause some trouble for us, because every time we have such a nested situation, we would have to mention what is the topology here. Are we looking at it as a member, as a subset of B or as a subset of X? And you can imagine the mess. But fortunately, there is no difference. The topology that A assumes by virtue of B is same as the topology A assumes by virtue of X. Okay, so that is the content of this lemma. Suppose X is a topological space and we have this nested situation as shown in the picture. Then the subspace topology on A borrowed from B is same as the subspace topology on A borrowed from X. It's a triviality. The lemma is not some difficult thing to prove. It's just that it is theoretically and philosophically important. Right? We should be able to imbibe this lemma. Math is not necessarily about being able to prove all the theorems in the book. It is about absorbing them and having a story in your head. I mean, it is also about that. It is about solving problems and also understanding the theory. It should become second nature, like a language. You don't need to consult every time. You don't need to consult a dictionary, right? It should become your second language. Anyway, so the proofs are very boring. Maybe I don't even want to write it. So suppose, or maybe I'll set up some notation at least. So let tau AX and tau AB be what? Self-explanatory notation. This is the topology that A assumes when we think of it as a subspace of X. This is the topology that A assumes when we think of it as a subspace of B. Okay? We want to show that these two things are equal. So let U be open in X. We want to show or we will show. So first claim would be claim that this is contained in the other guy. And this is what we are proving now. So how do we do it? We want to pick an arbitrary element here and show that it is here. So to pick an arbitrary element here, we pick an arbitrary open set in X and intersect that with A. So then, I want to show that U intersection A is in this space, but this is very simple because U intersection A is equal to U intersection A intersection B. Because A intersection B is A. A is contained in B. So A intersection B is A. And this is equal to U intersection B intersection A. But this is open in B. By the definition of the subspace topology on B, this is open in B. And therefore, this thing is in that guy. This is in that guy, and we have shown this containment. And similarly, the other containment. So we will pick an arbitrary element here and show that it is here. To pick an arbitrary element here, we need to pick an arbitrary open element in B. So to pick an arbitrary open set in B, first you pick an arbitrary open set in X, and then intersect that with B. So we want to show that U intersection B intersection A is contained here. Right? We wanted to pick an arbitrary open set in B and show that its intersection with A, which now becomes an arbitrary thing here, is contained in the other guy. Right? So I hope this is clear. Like, I'm just unraveling the definitions and going a little bit fast. But is it true that this is contained here? Well, again, we are seeing a B intersection A here. So what is this? This is the same as U intersection A. So we want to show that if we pick an open set in X, this thing is here, but that is clearly there by definition, so that holds. So this is about the triviality, but it's important to realize. Okay. So therefore, when we have, as long as we have a subset of a topological space, we have a natural topology on it, and we do not need to worry about various relationships. Whatever, I'm sure we are able to appreciate the importance of this. Okay. I think this is the last point. This really belongs in the second lecture more properly, but I will do it here. It's a very long lecture. Suppose X is a topological space and A is a subset of it. Then the subspace topology on A is the coarsest topology on A, which makes the inclusion map continuous. Right? So we mentioned in the philosophical aspect that we at least want this to be continuous. And we noticed that just asking for the continuity on it was way, way insufficient, because you could endow this with the discrete topology and still this would be continuous. But now this lemma shows that if you insist that the least expensive topology on A, which makes this continuous, is really the subspace topology. And that, in my mind, gives more meaning to the subspace topology. Right? Defining things in terms of maps is far more meaningful in general than just writing them down in some description. So this is how one should perhaps think about the subspace topology. It is the least expensive topology on A which makes the inclusion map happy. Okay? So here is the proof. So let tau A be the subspace topology, and theta A be the coarsest topology, which makes inclusion continuous. Okay. So first claim, we claim that tau A is contained in theta A. Okay, so fix some arbitrary open set in X. Then, since the inclusion map is continuous under the topology theta A, this is open, or this is in theta A. Right? Under theta A, the inclusion map is continuous definitely. It is the coarsest topology that makes theta A continuous. So the inclusion map is continuous when you equip A with theta A. And if U is open in X, the continuity of the inclusion map immediately tells us that the pre-image of U under the inclusion map is there in theta A. But what is this? This is the intersection of U with A. Right? So what have we shown? We have shown that whenever we pick an open set in X, U intersection A is in theta A. And that shows this containment, because an arbitrary element of tau A looks like this. To pick an arbitrary element of tau A, you just pick an arbitrary element of X and intersect that with A. So this containment was trivial. For the other direction, yeah, what about this? So to do this, just note that tau A is a topology that makes the inclusion continuous. Note that the inclusion is continuous when you equip A with the subspace topology. This is an exercise. I don't know if I said it earlier, but I should have. But anyway, this is an exercise. And since tau A makes the inclusion happy, and theta is the coarsest topology that makes the inclusion happy, tau A is finer than theta A, and hence this containment holds. So both directions were trivial. But again, this is not about the difficulty of the proof. The lemma is a meaningful lemma, and we should absorb the lemma, right? The philosophical aspect of it. All right, so I hope you followed that, and I think there is nothing more, thank God. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.